Alright, welcome back to lesson 9, the final lesson in the first unit, and it's projectile motion. So what's the goal today? I can break down a projectile's motion to x and y components and apply the kinematics equations appropriately to solve real-world applications. So projectile motion is simply the study of objects that move in 2D. So what we're going to be looking at is dropping versus throwing. Dropping versus throwing. So if you want to give yourself a bit of a sketch here, I'm going to look at a situation where we drop the math teacher from the top of a building versus throwing them off the top of a building. Okay? So what happens as the teacher falls toward the ground and just being dropped? I'm going to represent his body with green dots. All right. As the teacher falls, the velocity will begin to increase. So if these are my velocity vectors, I'm going to draw them bigger and bigger as he falls because gravity is pulling him downward. Okay. So let's make that as a note. Velocity increases as object falls. All right, so now if we look at the situation where the teacher is thrown off the side of the building, not very nice by the way, so try to keep those dots kind of in the same altitudes or same heights. There, finally, right there. So if we throw the teacher off the top of the building, what happens to the teacher's velocity? Well, let's look at the downward motion. What's happening as the teacher falls? Is there any difference between being dropped off and thrown off? All right, and the answer to this, of course, is no. The velocity, you're still being accelerated down at the same rate or the same velocity, so those vectors are the exact same in the downward direction. What about horizontally? What about horizontally? So if the teacher's thrown off, okay, what's happening to the horizontal velocity? Well, if I was thrown off and I was moving at 5 meters per second off the top of the building, then at this point, I'm still going to be doing 5 meters per second. This point, I'm still doing 5 meters per second. And this point, I'm still doing 5 meters per second. Why is that? Well, I have no jetpack. I have no way to accelerate. I have no engine. So I have to, whatever velocity I took off horizontally, I'm going to maintain that velocity all the way through. So the difference between dropping versus throwing is going to be, first of all, the horizontal displacement will be different. All right. But you'll find that time to impact is going to be the same because we're falling at the same rate. All right, so if we have over here delta t, maybe I'll put it in the next slide. That's what I'll do for my summary. All right, so moving over, and this particular lesson or video has an applet tied to it, so I highly recommend trying that applet out just to do the comparison. So important properties of projectile motion. Okay, first one is objects fall at the same rate regardless dropped or thrown. So what does that mean? It means that flight time is the same. Flight time is the same. Okay, so if I drop a ball and roll a ball off the desk, it's going to be in the air the same amount of time. It'll land at the exact same moment in time. All right. Number two, projectiles have no acceleration, no acceleration horizontally. And I'll put in brackets here, because in this course, I'm not going to, they're going to have a uniform motion horizontally. And I'll put in brackets unless they have a jetpack. All right, so if you have a jetpack on, it's a whole different story, but we're not adding jetpacks here. So for the horizontal, acceleration is equal to 0 meters per second squared. Okay, vertical is always 9.81. So those are known values. Okay, so that's true for all of them. Next, in your grade 10 math course, you spent some time on parabolas. And what we find is if we launch something, soccer ball, tennis ball, baseball, they all follow parabolic motion. All right? So projectiles follow parabolic motion. Okay? Which means they have a vertex. If they follow projectile motion, they will have what everyone here knows as the highest point, or the vertex. All right. So at the vertex, what happens? Well, an object was moving up. When it reaches that highest point there, okay, when it reaches its highest point, it starts to fall down. So for one moment in time at that point, your vertical velocity is 0. So at the vertex, the vertical velocity is 0. So just for one brief moment in time, that object is going to come to a stop and then fall back to Earth. Okay, so projectiles follow parabolic motion. At the vertex, the vertical velocity is 0 meters per second. So there we go. So those are some of the more important or key properties of projectile motion. Now what happens if something is launched at an angle? Well, the whole reason that we kind of did vectors is not only for Unit 1, or sorry, for Unit 2, but it's also important for Unit 1. So let's say that we have a cannon that fires an object at that angle. So it has this velocity. Well, we can only work in 2 dimensions. All right, so projectile motion only works in 2 directions. So we want horizontal, and we're going to want vertical. So I guess I can go sideways here. We want vertical. So if I look at this particular V value, yes, it's 2-dimensional because it's on a piece of paper, but I want 2 dimensions that I am comfortable with or familiar with. So what we do is we break this green vector into its components. It's the same as what we've already done. So X component, Y component. Okay, so we break it into X and Y components, break it into 2 parts. If we know the launch angle, then we can calculate our horizontal velocity. So V horizontal is always equal to magnitude of V, okay, cos theta. And the vertical velocity, VV, is equal to magnitude of V sine theta. So we are taking that vector notation. Remember we said that vector V equals vector V cos theta I plus magnitude of V sine theta j. Those 2 components, we're using those as our horizontal and our vertical velocities. Because what we're going to do for projectile motion, we are going to split projectile motion into 2 types of questions. We're going to break it into a vertical and we're going to break it into a horizontal. So here we start into the examples. Circus clown is shot at 40 meters per second horizontally out of a cannon from the top of a 100-meter high cliff. So I'm just going to give myself a diagram here to follow it through. So my clown is fired horizontally, which means that he had no initial vertical velocity and plummets down here. Okay, diagram's probably a little large for what I really needed. So what I'm going to do then is I'm going to break it into two parts. And I encourage you to do this as well. We break it into a horizontal and we break it into vertical information. So you're breaking this into a two-part question regardless what it's asking. What do we know? Horizontally, we know that the velocity, horizontal, was 40 meters per second, and based on my picture, it's to the right. Well, what was the initial vertical velocity? What was the vertical velocity? Well, if he shot perfectly horizontal, he would have no vertical velocity. You have to either throw something downward or upward to have a vertical velocity. So, down or up doesn't really matter because it's the zero vector. Okay. What other information is given? Cannon from the top of a 100-meter high cliff. So this cliff is 100 meters in height. That's vertical information. So this is where you got to decide, where is your reference point? Where's your reference point going to be? Most people make the reference point from the launch point, which is fine. Now you have to decide which direction is positive. Still, I always assume upward and to the right is positive, and you do not have to follow this convention. But I always like to be consistent with my x and y axes. So if that's the case, that means that my displacement will be negative 100 meters. Okay, or it'll be 100 meters down. So maybe we can do that to start with. 100 meters down. And that's all the information that's provided. So what else do I know? Well, vertically, I know that acceleration is going to be 9.81 meters per second squared down. They're not going to give me that in the question. Okay, that's just something I need to know. How long is he in the air? That's the unknown information. So it is the same for both horizontal and vertical. Delta t is the same. I look at, where do I have enough information to solve this question? Do I have enough information horizontal, or do I have enough information vertical? When I look at I need another piece of horizontal information. I need the d, the displacement horizontally, in order to solve for time. On the other side, I have a v1, a d, an a, and a t, so I have enough information to solve for that. It's just a matter of decoding and finding the correct formula. So I find that delta d equals v1 delta t plus 1/2 a delta t squared. So using that information, remember I have upward as positive, so I have negative 100 equals, my v1 is going to be 0, delta t plus 1/2. Acceleration is also down, so it's going to be negative 9.81 delta t squared. So I do like this because that goes to 0. So I'm only going to have one delta t to solve for, and I'm going to divide both sides by 1/2 negative 9.81, 1/2 negative 9.81. I know I have negatives on both sides, so the negative signs are going to cancel out. And I get an answer of 20.4 is equal to delta t squared. Taking the square root of that, I get 4.5. 4.5 seconds. So therefore, the clown is in the air for 4.5 seconds. All right, I'm going to finish up the note in the next video so that I'm not rushed through finishing up this example, and I have some time to explain the next one.